There's really no excuse for not knowing how to write chemical formulas at this point. This is definitely something that you should be able to do. So here's how you start this. You take this type of starting point here. You want to look at, are you dealing with two compounds? Are you dealing with a compound and an element? Are you dealing with a single compound by itself? You know, that's going to tell you kind of, or give you a clue if you understand about the patterns of what's going to happen on the other side of this arrow. And so you can start by just writing the formulas for these compounds. And so ammonium sulfide, like this, reacted with plus hydrochloric acid. And you're supposed to predict what happens on the other side of the arrow. Your options are, it's a double displacement reaction, it's a decomposition reaction, it's a synthesis reaction, it's a single displacement reaction, or it's a combustion reaction. What do you think it is based on what you're looking at here?
Double displacement.
Double displacement. How did you know?
Because it both has two elements in each bond.
You have like two ionic compounds that you can actually see how they would kind of break apart and reform on the other side. Go ahead and start there. Start with that. You don't have to write out the names of the compounds. Go ahead and just balance the formulas. Now you've got to mentally take them apart and reassemble them on the other side. So you got to split these up and split these up. What that means is that you may not, just because you have two of these over here, don't go assuming that you're going to have like that over here. Okay, don't do that. You got to mentally go, okay, ammonium has a +1 charge. Chloride has a -1 charge. You're going to put the positive one for this compound, the negative one for this compound. So then you go NH4Cl. Notice I'm ignoring the fact that there were two of these over here. We're going to clean that up and we balance it out later. And then the other one is going to be taking these two here. Now sulfides are a -2 charge, hydrogens are a +1 charge. We have that. So there's our two products there. It's not balanced yet, and then we have to go back and say, all right, is this a gas-forming reaction? Is it forming a precipitate? What is in solution? So these are probably going to be solutions, unless this was a solid. Let's just say I have solution of ammonium sulfide and hydrochloric acid are reacted. So these are two aqueous solutions. It's implied by the word acid that that is aqueous, but I'd have to tell you that. So that would be a question that you could ask if you're thinking that you're like, is this an aqueous solution or not? I might be able to tell you.
Do we have to have like the state of matter inside on the test?
No, but it will tell you if you have to use net ionic reactions or not. Remember, you have to show them as dissolved ions in solution if they are dissolved in solution. Right? So these then, if this is aqueous and this is aqueous, they would not, this is a complete molecular, this is not net ionic at this point. One thing, it's not balanced. For another thing, it's showing dissociate, it's not showing dissociated ions. So you would have to put a 2 in front of here and a 2 in front of here first, and then we've got to balance, or divide it all out and make it into the ions. So remember, complete molecular equation is this. Ionic equation is going to be to split those all up into their separate ions.
What did you call that? The one with the separated?
This is complete ionic.
Oh,
Now I'm writing it out to show you how it breaks apart. You don't have to show these steps when you do these problems. But if you're not getting it right, and some of you are probably going to get annihilated on this, on the next test. Because we haven't worked on it a whole lot since then, and this is just, a skill that you either know how to do it or you don't. But there it is. You split them all up as separate ions. Now ammonium chloride, would that be in solution or not? It would, yes, it would be in a solution, or no, it would not.
Wait, what?
Is this soluble?
Yeah.
Would this be dissolved?
Yeah.
yes.
Yes, if it is soluble, that means you would show it as ions. It would be dissolved. So then over here, this would be dissolved. Now, if you weren't sure about this one, this is an extremely weak acid. And I'm not going to test you on this. Like your question, your reactions tomorrow are going to be a little bit simpler than this one. But this is actually your product over here. You would show that as a weak acid. We'll learn about why that is later, but that stays intact. So now you go and cancel off anything that stays the same on both sides. Yes?
Sorry, it's the one that is not going to dissolve that we keep.
Right.
Okay. So we should memorize those solubility rules again.
You should remember what is, like, usually the one that's not, or the one that, sorry, the one that is soluble will be obvious. So you're going to be like, okay, well, that was dissolved, and that one has to be intact, because that is definitely a soluble compound. You're not going to have a no reaction where everything just stays dissolved and it just stays in water. There's always a reaction. And so one reason, and by default, this is going to stay intact because this already was shown to be a soluble compound. But like I said, the reason is because this is what we call weak acids, and weak acids do not dissociate in water. They stay intact in water. It's kind of it's a special type of reaction that we're going to learn more on later. Okay, so then the final step would be to, eliminate anything that's exactly the same on both sides. Now, a lot of you guys were, in the last go-round with this stuff, striking out the exact wrong thing. Remember, anything that doesn't change gets taken out of it. It's like having a polynomial where you have, x plus y squared plus 3 equals z to the 4th minus y plus x. And you're going to go combine like terms. Well, the x's are going to end up dropping out of both of these terms because it's both the same on both sides. It's just algebra, you guys. And I know you've all made it past algebra 1, 2. Theoretically, anyway. I didn't check, but so that's what you have to think about when you're doing that. Is that you got to think of these as being like terms in a polynomial.
So, Miss Becky,
Yes.
so if like say instead you had, I don't know why. Okay, so like for B, on the left side, for the hydrogen sulfide gas, like when I broke it down, you have H2, like, like a subscript, and then on the other side you have 2H. You might cross those,
No.
you don't cross those out,
Nope.
right?
Nope. Nope, because this is showing it as an ion, and this is showing it as part of a molecular compound.
Okay.
Now, keep in mind, I want you to think about those ones on that reaction prediction -1. Some of those are pretty tough. Like, definitely do not need to know about phosphorus 5-oxide powder sprinkled over distilled water. I'm going to pretty much stick to, for reactions for you guys, your basic, precipitation reaction, single displacement reactions, combustion reaction. I want you to kind of get a good, get some good practice with the major categories. I'm not going to be trying to throw any weird, obscure reactions at you. And I probably will be avoiding a lot of acid-base as well for now, because you don't know that, so we don't learn that until like chapter 15. So we're not there yet. But these are just random reactions here, so some of them are a little bit harder than others.
Do you have an answer key?
Yes, I do. Any other reaction questions?
Can I ask a question on the other chemistry?
Sure.
Okay, I had a few, but 2002 question 3 part C, where you have to draw the 2 different types. I got like 1 different. Are those isomers, or what are they? When they have the same number of electrons, just different formations.
Okay, so yeah, you start with pentane.
And then how can we change that? So I connected the carbon in different formations.
Right, so the isomers for this, yeah, so you do like, like this kind of thing. Okay, yeah. That's one of the isomers.
And then one would be a carbon.
And then you have one where you have a carbon in the middle. Those are the only two isomers for pentane. The isomer, iso meaning same, isomer is the same formula put together differently. You guys got to mess around with that. It was the model kit lab that you were doing. The thing about this is that, like, this is not an isomer. You did this. You just put a kink in it. That's not an isomer. All you did was just take that chain and like bent one of them down. You didn't change the structure. You didn't take it apart and put it together differently. All you did was like just take one and bend it the other direction, or bend it up, or do it where it's kind of doing like this kind of a thing.
Did you put that one carbon to the left one? Like, did you put that carbon that's down on the bottom right, move it over one to the left?
That's the same thing as this one.
Really?
Yep.
Oh, yeah.
Right? If you take this and you rotate it up here like that and turn it, that's why having the model kits is really helpful. Because then you build it, and then what you do is you literally can pick it up and move it around and lay it back on top. You're like, oh, it's the same one. This is an organic. This is about as complicated as this is going to get, because this is a huge organic chemistry thing, which some of you will take early on in college because you've taken this class already. So that's like kind of the next thing that's coming is structural and organic chemistry. Yeah.
For the next one in the 2002 part, it actually defines the hybridization of ICL4 negative, and has a hybridization of sp3d2.
Yes.
Will we have to do into the D's on the test?
I don't think so.
Why does it have the D2?
Because
Because I just put sp3 because it has 4 electron clouds.
Because iodine, ICL4, right? I'm just kind of, again, modeling that process I taught you. You've got iodine and 4 chlorine, so that's 5 times 7 electrons is 35, plus 1 is 36 electrons. So iodine is the central atom. You put chlorines around the outside. And then you go ahead and put your lone pairs in there. Make sure your lone pairs are obvious to me. I mean, you don't have to go like our cartoony about it. But don't do the little, I don't know if you know what you're doing or if you're just scribbling on there and hoping that I won't notice. But, you know, make sure you're deliberate about your lone pairs of electrons. Okay, so you have this. Now when you stop here and you add it up, you have 32 electrons. To 36. 33, 34. It doesn't matter where you put them, just put them in pairs, 2, 5, 3, 6. Or you can put them across from each other if you like.
Is that one of the expanded documents?
Yes. Remember I had psi, xd, what was the other one?
I just create the I remember it. I was trying to DSXE.
Wait, I'll tell you 1 second. Wait.
You said
I've seen
sorted.
SE. SE? Yeah, there was no. Yeah. And then form after 4 single bonds with oxygen is ClBr. Okay, so it only becomes necessary to do this because you don't have enough electrons. So if you had 32 electrons, you had 4 left over that you had to put. You can't put them on the chlorine. You already assigned as many to chlorine as they can go. So you're going to assign them to the iodine. Which means you have S, P, 3, and then the other one's, so it's D2. Question? Question?
Is it ever,
Go ahead.
is it ever possible for it to have like more bonds? Like,
Yeah, but chlorine can't do that.
okay. But iodine, could iodine? How do you know? It doesn't have
It's gonna, it would come up in the event that you had to make it work for a structure that you were given. I don't know if that makes any sense, but you wouldn't need to do that until you had to do that because you had to make the electrons work out. That would be the only time that you would have to do that. I can't think of an example right now off the top of my head.
Okay.
It's not very common, I know that.
In my notes, you didn't write down the D2 because you said we don't have to do that.
I don't think, this, like I said, this is an old question.
Okay.
So, like I said, I don't, when Greenhouse asked me that, I don't have the test in front of me right now, so I don't recall exactly. I'm pretty sure, no.
Because I don't even know what that means.
It just means that you have 4, 1, 2, 3, 4, 5, 6 clouds. So that's, and then, so when you have something like PF5, and you're drawing that one, and it does the, and you're like, oh, well, okay, so I drew 5, S, B, B, C, D. That's what they're saying about that.
Okay.
And it is, it's a throwback, I just did take the question off.
Can you do that additional question?
Really?
That one is just regular.
It's 5 plus 4, 1 minus 1 is 8.
Right, 2, 4, 6, 8.
Oh. Okay, never mind.
Okay, tetrahedral. SP3.
And the other one we just did was a square.
Square planar.
Square.
1999, part 2, it talks about like bond length. Could you go over that?
Sure. Okay, so one thing, think of is terms of bond strength. I'll draw this like this.
Because it has 2 things. So
So the energy it takes to break the bonds increases as you go from a single to a double to a triple.
Why
Right.
is this triple more harder to break? Wouldn't it
Yeah.
be easier because there's more repulsion, because there's more electrons just sitting in the same place?
It stores more energy. Think about it, it's got more potential energy stored in the bonds. The length decreases as you go down between those 3. So they get closer and closer and closer. You're talking about a massive negativity in between these 2 positive nuclei. And so it kind of, the whole thing electrostatically is held together a lot closer, which makes it harder to break, which is kind of, they just kind of go together, those 2 properties. So what we're looking at here, if you draw the structures correctly, then that will lead you to the right answer to make about this. So you've got carbon dioxide, and then we've got carbonate. So there's that, which you should go, there could be a resonance structure, because there is. You have this double bond here. Now if we colored this one red, this one blue, and this one yellow, at any given time, that double bond could be on the red, the blue, or the yellow. So you could draw any of these structures, and these are all valid possibilities. And in fact, those electrons, being the wacky electrons that they are, will in fact move around in between these locations. So you've got this version, and this version. And all I've done is just move that around. And that's not the same thing as an isomer, where you just take this up, pick it up, and put it down on there. But you're literally, like I said, if I were to label each of those oxygens, that double bond just kind of rotates in and around between. Because what happens is that you will get one of these electrons on this side over here. This carbon, by virtue of this electronegativity, all those oxygens are very electronegative, all the electrons are kind of going out towards the oxygen. This is a slightly positive carbon over here, if you want to look at the dipoles that are happening. What this is like an internal nucleophilic attack. I know that's kind of a weird word. Nucleophilic attack usually refers to something other chemical coming in and doing this, but what happens is that these electrons then come in and go, oh, awesome, which then pushes these out to this side, and you end up with a different, now you have a double bond over here, so that would be this one. So that. And then maybe these go into there and push these electrons out this way to that oxygen. And so you end up with all of these happening at the same time. Here's the upshot. If that's happening constantly, what you end up with is this. Those little dots, where you're showing kind of the pathway these electrons are going to take. You wouldn't draw this way because you're not really sure on what you're saying, but if you have those electrons constantly zipping around in there, really what you have is a 1 1/3 bond going on between all 3 of those oxygens in the carbon. So essentially, that 1 1/3 bond was called a bond order. This has a bond order of 2, both double bonds. Not 2 bonds. Right? So based on this logic and the fact that really what you have is a bond order of 1 1/3, that's what's going to make these ones be longer because of the resonance structures. Yeah.
That makes more sense, but is it possible for the carbon dioxide to have a double bond, a single bond, and a lone pair on the carbon?
Probably not, because the carbon isn't electronegative enough to hold those lone electrons
Okay.
compared to the oxygens on either side. So it's likely that the electrons would just skip over. But you don't have what you call a conjugated double bond system where you have a single bond and a double bond, because that's when you get that movement happening. But if they're both double bonds, it's pretty stable that way. It's not going to really do much, and that's why carbon dioxide is so stable. I mean, it's a gas. It's not polar at all. It's really hard to get it to liquefy. You freeze it, you get dry ice, but then it just goes right to a gas form. It doesn't even go through a liquid stage. It's so non-polar. Yeah.
So in that question, when we're describing how double bonds and triple bonds take up less space, how do we, like, what language do we use to say, like, why?
It's a really good question.
Besides, like, gravity.
No, you would say
Holds it in tighter, so it's shorter.
the bonds are shorter. You could just say triple bonds are shorter than double bonds are shorter than single bonds. Carbon dioxide has 2 double bonds. Carbonate, you remember, mentioned both things. Carbonate has a double bond, but it also has these 2 single bonds. And because it's a resonance structure, that second bond kind of rotates throughout the whole structure. So at the most, you have this bond character. Right? Does that kind of make sense?
Yeah.
You would just say it's about a 1 1/3 bond, which would make it longer than, you've already used that logical argument, and you can use that. That's like you're using a fact.
Definition of resonance structure, please.
It is a structure of an element that shows different electron arrangement.
So it's not an isomer.
Not an isomer. Isomer is literally built differently. This is built the same, just the electrons are shown in different locations. And it always really has to do with with like oxygens bonded to some other element, some other nonmetal, like phosphorus, sulfur, nitrogen, carbon, those ones. Usually are going to be the key players in that, and then you have oxygens bonded to it. Like nitrate is one of the ones that we were looking at yesterday. Phosphate, sulfate, sulfite, all of those ones have, you could draw different resonance structures for that. And it just means different ways of showing where the electrons are located. Isomers are literally the structures put together differently.
So an example of a resonance structure is putting a double bond in a different place.
Yeah.
Okay.
Yeah, like you have, these are all oxygens, and what you're saying is that the double bond could be on this oxygen, or it could be on this oxygen, or it could be on that oxygen. And you're not showing it as an isomer, you're showing it as literally like you could take those oxygens and somehow distinguish them from each other. You would see that. And the way that theory came up was that they were doing probably spectroscopic analysis on this, of looking at the way that they refract light, literally how molecules refract. And they were noticing that, or doing like an NMR type thing, where it's like a nuclear magnetic resonance, and they were able to see Oh, this isn't they couldn't pick out one double bond. It was equal among all of them. So that was the theory, is that you have this resonance structure there. Yeah.
2 questions. Does the length decrease because of Coulomb's law? Because the charge gets, gets more negative?
You mean, is like what
The length of the
first,
bond.
the chicken or the egg? The length, the distance between the nuclei
Yeah,
gets
the-
smaller?
Well, the charge goes up, so bond is close, the gap is moving closer. Keep things from, because, both sides stay the same.
Charge goes up.
Right.
You're talking about like the number of electrons in between them?
Right, so the negative one would go up. The negative charge would go up, the positive one would stay the same in order to do it. Well, that's-
I think you're on the right track with that, yeah.
But,
And you're saying if the energy is, the energy of that is, but the energy goes up also.
Well, it's just, if
So the distance decreases and the charge is going up, so the energy goes up. So that's not necessarily a cause.
The force between them. Or no, it's force.
And the energy increases.
Well,
Like if you look at those tables of bond energies, the ones that are like, if you look at this one, these 3 bond energies, I forget what page it's on. In here somewhere.
350.
The one that has the table with all of the. Right, a carbon-carbon single bond is 347. A carbon-carbon double bond is 614. And a carbon-carbon triple bond is 839. So the energy, the bond energy increases.
Are you still answering the question?
A little bit, I don't know. He was just making a comment, trying to come up with a cause and effect of why.
the other thing I want to know is, I thought that because all the electrons were all in one place, that the bond would be bigger. Like a triple bond would be bigger than a single bond because all the electrons are in one place. Like all 3 of them, they would repel each other away.
Oh, they would, well,
Maybe because the pairs are like kind of looking, well, are they looking or are they happy when they're pairs?
they're bonded, so you've got them, their orbit, or their molecular orbitals are overlapping. So there definitely is room to go in between the 2 atoms that are bonded between. They tend to stay in between them because they're in between the 2 positive nuclei. So it's like, hey, it's a good place to be. Yeah, there is a certain amount of instability and energy inherent in that because you do have all those electrons in the same place. But that's kind of why, if you think about a carbon-carbon single bonded fuel, which this would be like ethane, ethene, ethine. This is acetylene. This is what they use for blowtorches. So yeah, it does give off a lot of energy and it's pretty flammable. These are still used as fuels in some way. You can use like ethanol. There's an alcohol group on the end of this and it's used as a fuel. And then ethene is just a double bonded version. But they are, I think, less and less stable or more and more flammable. But that energy is stored in between those 2. So it literally like compacts them in. So they're shorter and fatter.
Yeah, that's what I was wondering. Like you said, the length increases, but I was
Between the
told
2
that,
carbons, yeah.
During the